Welcome to our final press conference of today. This one is called New Insights into Boulder Transport by Major Storms. And we'll have three speakers who will speak in this order. Max Engel, he's research assistant at the Institute of Geography of the Universität zu Köln in Cologne, Germany. Andrew Kennedy, he's associate professor at the Department of Civil and Environmental Engineering and Earth Sciences at the University of Notre Dame in Indiana. And Robert Weiss, associate professor, Department of Geosciences, Virginia Tech in Blacksburg.
All right, thank you very much. Thank you for having invited me to speak on this panel as a coastal geomorphologist and non-geophysicist. Super Typhoon Haiyan in the Philippines was one of the strongest tropical cyclones on instrumental record, and it caused extensive flooding in low-lying coastal areas such as the coastal plains south of Tacloban on Leyte. It caused more than 6,200 fatalities and billions of infrastructure damage. We conducted a field survey to document geomorphic changes and sediment deposition, such as sand sheets, you see them here, and boulders. On the island of Samar, we found dislocated boulders of up to 180 tons with main axis of up to 9 meters. And this is a pretty unusual pattern for tropical cyclones, and these might be the largest ones so far documented for recent storms. We found boulders moved up to elevations of 10 meters above mean sea level, and we currently think that the largest boulders were probably not moved by storm surge or regular storm waves, and this differs a bit from the time when we submitted the abstract, some of you might have noticed. This one is the largest boulder that we found. It's located at the margin of a lagoonal reef, a shallow one. It's a very peaceful and calm environment most of the time. And it's located on an inclined limestone platform with moderate surface roughness. Oh, let's go back. It experienced longshore transport for about 45 meters based on pre- and post-typhoon satellite images in northward direction, and its main axis is perpendicular to the transport direction. Other smaller boulders were quarried from the cliff edge, transported on top of the uplifted carbonate platform in a sliding or saltating mode, and those boulders on this uplifted platform have a different angle of transport than those which are in sea level position. On the map you can see the study site, which is north of the track of Typhoon Haiyan in the central Philippines archipelago. Transport of the boulders, apart from pre- and post-typhoon satellite imagery, there is multiple evidence for unequivocal evidence for dislocation of the boulders, such as wood jammed under the rocks or fresh barnacles, which indicate that the boulders have recently been dislocated from intertidal position. You see these downward facing grass patches. You see also these roots and soil staining on the surface, on the now exposed surface, the former bottom side of the boulders that indicate that some of the boulders have been overturned. You see the scarps, the fresh scarps at the cliff edge, and impact marks on the limestone platform and also on tree logs that help us to exactly trace the pathway of the boulders from their source to their current position. So some implications. Giant boulders that are commonly associated with tsunami transport can be moved during storms. This is not an entirely new conclusion. It has also been made, for example, by Robert Weiss, sitting here on the panel in his paper in Marine Geology in 2012, mainly based on a theoretical approach. So longer wave phenomena may be associated with extreme storms to generate even tsunami-like flooding patterns, and maybe also be responsible to shift giant boulders which are in sea level position. Andrew Kennedy will give more details on that when he shows his two-phase model. Smaller boulders that we found in elevations of 4 to 10 meters are probably quarried and dislocated by the extreme wave setup. There is a slightly different transport angle, which might refer to a stronger deflection of the regular storm waves, but this is just an hypothesis. To wrap it up and also to lead over to Andrew Kennedy's presentation, I would like to show this video by aid worker Nixon Jensis from Plan International, who took this video in the same municipality where we studied the Boulder field. And what you can see here is a tens of seconds to minute long, one-directional, high-velocity uprush of waves that we would rather associate with, or that we resembles more what we know from survivor videos from the Indian Ocean tsunami in 2012 than what we would anticipate for a tropical cyclone. And residents reported on 2 to 3 of these waves during interviews. Thank you very much.
Thank you. I'm going to continue on the theme that Max started on. I'm going to start by talking a little bit about the same storm at a different location, and then I'm going to move on to show some modeling to show how these giant boulders actually started moving. And we're at a slightly different site. Here's the track of Haiyan. Many of you will remember Tacloban was where the very bad things happened to the city. This was Max's site, and we were a little closer to the track right here. And a hindcast at our site, just offshore of our site, had a significant wave height of about 19 meters at maximum, which is extremely large, one of the largest hindcasts ever seen. We saw run up to about 200 meters inland and 9 to 10 meters elevation, similar to what Max had. And we were actually on a Japanese-led survey, not to look at boulders, but to look at the run-up. And we were doing one of our transects. We were walking along, and it's very hot, and climbing over all sorts of down trees. And we came across things like this in one particular region. This was one of the largest boulders. This is at 7 meters elevation, so something like that above ground level. It's very, very high, about 100 meters from the ocean. We finished our run-up survey, and we actually came back later. We made a special trip to come back and see what these boulders were. This shows some of our survey. Just in this small area, there are hundreds and hundreds of boulders, not all that large. In fact, they're all smaller than that. But that was just in a very small area. We only sampled some of them because there are just too many. There are many hundreds more. And in fact, if you just went a little ways away, places we couldn't get to because of lack of time, we can see much larger ones on satellite images, very similar to what Max showed. Here's one 7 meters, 9 meters, 8 meters long. These are just a couple of kilometers away that we can see that they appear on satellite images. Now, because we didn't go there, we can't demonstrate that they arose from that storm. The ones we surveyed by hand, we can. But the question is, for both the ones we surveyed and the ones that we see on the satellite, what are the mechanisms driving this? Obviously, it takes very large forces to move these. So we performed some modeling. And the way we did this was we had a wave model. And the wave model looks at the waves as they come into shore, they break, and they run up, going up like you saw in that video, create large infragravity wave groups. The wave that destroyed the house, it's called an infragravity wave. And we had forces and friction and so on to move the boulders, and we looked at this. I'll say that these are not three-dimensional. We're working on that, but these are still two-dimensional results. The easiest way to show this is just to let you see the video. Hopefully. There we go. Okay, so you can see the waves coming in. This is much faster than normal, obviously. Here's the bathymetry. Sea level is about here, goes up here. The numbers are different size boulders. 1 is the smallest, 5 is the largest. The middle panel is simply a close-up of the top panel so you can see a bit better. The bottom panel shows the distance over time. And you can see that if you look about here, it's very intermittent that this is inundated. It goes down and up, down and up, down and up. And it's only when the infragravity run-up gets up to these larger heights that it's actually moving these boulders. The smallest one, number 1, you can see it moves the most because it's the smallest and it's easiest. The biggest one, number 5, doesn't move very well. But it's most of the time they don't move at all. It's when these very, very large groups come through, then they push things up. Once they get to near the top, then they just keep going shoreward. This is not the entire storm simulation. We have done those, but it takes too long. This is just an example, and it's just started over again. So the take home is that the transport, especially higher up, appears to be done by these low frequency infragravity wave groups that intermittently push very, very high up and transport the boulders. Implications. One thing, when we first saw these large boulders, one of the Japanese who'd done surveys on the 2011 Great East Japan tsunami said, this is a tsunami rock. He didn't believe it was caused by a tsunami, but if they saw it in Japan, that is what they would say. And if this had happened 200 or 300 years ago and we didn't know this was caused by the storm, and people saw this, they would probably believe it was from a tsunami. And it wasn't. So it may be very difficult to distinguish between these two, which is a complicating factor when you're looking at coastlines and what happened in the past where you don't actually have records. The other thing is that the onshore transport can be driven by this low-frequency infragravity bore run up to hundreds of meters onshore. One thing I'll say is this is not well considered in design standards, which is something that really needs to be addressed. And the other thing, the final thing, is that the observed transport, we saw many boulders that appeared to have been sitting on the beach or buried on the beach and then were uncovered and moved further up. So the transport may be from more than one storm, cumulative over time. And I'll finish there and pass it on to Robert.
All right, thanks very much. I'm going to talk about something very different, not about an explicit example. I'm going to do more like a theoretical analysis of this. And the reason why we care about boulders is they are very important for hazard assessments and hazard perception. If large boulders are moved, we usually think large storm or large tsunamis happened. And boulders are good evidence of those disasters because they can only move by either large tsunamis or large storms. More common marine processes cannot move them. They're simply not energetic enough. So if you think about these two extremes here, the boulder and the sandcorn, drawn on the right for scale, the sandborn can be moved by any wave that occurs on the beach. The boulder only can be moved during a storm and tsunami. So they're really good for figuring out how many tsunamis or how many storms occurred in a certain region that then can be used for hazard assessments that are very, very important for planning and policy purposes. So they're good for that. The problem is that in our analysis, we found out that if we use traditional methods and compare it to a relatively new method based on a more physically complete sort of system of equations, then we found out we have a variance error between 35 and 78%. It's not so much that the error is there, it's that we cannot predict what error actually exists. To give an example, I can tell you I created a method to estimate your size. Let's say you're 6 feet tall, but actually I don't know that, and I don't know if you're male or female or what your weight is. You may be only 5 feet tall. I cannot tell that. That's in the error. Or you might be 10 feet tall. I don't really know. And that's sort of the problem that we have with these hazard assessments at the moment, because we have a varying error that we cannot predict which magnitude it has. And that's of concern, because that has implications on the results of implications of the hazard assessments and perception. Is that satisfactory? I don't think so. So we need to work on making the way better, and that's sort of my conclusion the conclusion of it. What we did is essentially these two things. We have a boulder on the left and a boulder on the right. Traditional methods usually just look at, does the boulder on the on the left move or not? And that's one portion of it. The other portion is, will the boulder actually move to a position from which it can be dislodged? If the boulder doesn't arrive there during one of these wave events, for example, that was described previously, the boulder will move back to its original position and not move at all. So we don't find evidence of the boulder to be actually dislodged. And that's the difference between these two methods. One is a threshold method where we just look at, is the boulder moving or not? And the other one actually looks, is the boulder moving far enough out of his pocket to actually move, or be dislodged rather. And you can see that in this sort of diagram. On the x-axis, we have the amplitude of a wave, or representative of the amplitude. And on the y-axis, we have sort of a time component. How long does the boulder move? And we have three different fields here, the red, the yellow, and the green field. In the red field, the boulder doesn't even move. The amplitudes are too small to actually start moving the boulder. The boulder is completely unaffected by the waves arriving. When the transition occurs from the red to the yellow one, which is usually associated with the forces are larger than zero, and then it starts to move. That's the first sort of method that was proposed. And then the second one, the transition from the yellow to the green, that's when the boulder actually starts moving, as we saw in the video in the previous presentation. And the width of this yellow area is actually the error that we have between these two methods. And that's the problem that exists essentially. So why is there GPU SPH modeling? We could just very simply do theoretical analysis, but from the video that you just saw in Dr. Engel's presentation, we saw there was more or less like a rush. It was not like a clear wave of 6 or 7 seconds that was associated with storm waves. There was like a surge coming in. And for that, we use numerical modeling to do that. I couldn't show you a video of this, but our model is what we call smooth particle hydrodynamics. It uses lower particles instead of water. It solves a very physically complete set of equations, and the cool thing is these equations are solved on graphic cards, so it's sort of like a gaming graphic card that we use. And with that, I thank you for your attention. Thanks.
Thank you, speakers, for your talks. And we'll open up the floor now for questions. And please identify yourself by name and affiliation.
Thomas Sumner, Science News. I'm wondering if there's any way to tell the difference between a tsunami boulder and a typhoon boulder?
Good luck.
I think it's very difficult.
It is very difficult. There are, of course, many observations after recent events, some of the recent large events, and probably also our observations, those of Andy and our observation, might contribute to this data set, but the patterns vary widely. There's a wide spectrum of sedimentological patterns resulting from both events, and they are overlapping a lot. So it's very, very difficult based on sedimentology.
Well, from a theoretical point of view, if you do a very simple analysis between the two waves, and you have a very long wave as a tsunami, very short wave, there's less than 10% difference in the wave amplitude moving between the storm and tsunami wave, moving the same boulder. And that's, in my opinion, way too small to be recognized in the field. I mean,
There may be other things,
yeah.
but just the boulders, it's difficult, I think.
For a boulder of this size to appear on the beach, it can't have gone unrecognized in the past by people who actually live there. So did you do any interviewing of residents in this area or look for anything in past oral or written records to see what has been recorded in the past? And sorry, Becky Oskin from Live Science.
Well, in our case, it was, we had, on the site that I was presenting, we had very little time. So we asked people around, but we were not able to organize a thorough interview session. So, but we didn't get clear answers. So, so the only thing that we have are the physical evidence that I was presenting, and also the satellite images. And this evidence, I think, is very clear.
Where we were, there weren't a lot of people that lived there. The best evidence, again, we have pre-storm satellite images that show a couple of boulders that were more seaward than the ones we saw. The small ones you can't tell. The small ones could have come from anywhere. The very largest ones are the only ones you can see on the satellites. And the pre-storm showed some large ones that were much seaward of where our big ones ended up. But there weren't really people who could tell us that.
Do we have other questions from the room? Any from the chat? Okay.
Could you explain in more detail, or maybe simpler detail, what it is about the wave that actually transports the largest boulders that makes it different from a regular storm surge wave? You're talking about it being maybe a little bit more tsunami-like as opposed to a regular storm wave. And I don't quite understand how to actually explain that to somebody who would be reading the story.
I guess the first thing is that they're bigger. Super Typhoon Haiyan was giant, and no one has good measurements, but it may have been the strongest typhoon ever to make landfall in the satellite era. So the larger storm breeds larger waves, which can move larger boulders to higher elevations. And then it looks like a tsunami when you're at a high elevation because you're used to that being ground, and then there's nothing happening, it's always dry. And then in these very, very rare circumstances, you have phenomena like Max showed the video of the house being destroyed. And it looks like you're dry, then you get these big low-frequency waves coming up, and it looks like a tsunami. It's actually the same phenomena as you would have for smaller waves, but they're just much smaller and much further down. They can't get to as high.
The problem with that is, Albert Einstein once said that we have to use what was it? Models have to be as simply as possible, but no simpler. And that's oftentimes, we are caught in that sometimes. We use too simple models to explain certain things. And for example, that video that was shown about the inundation was one of the first videos that was actually shown of a storm. We envisioned oftentimes just the impact of waves, and we used very simplified ways of dealing with those. And then it turns out that nature is not as simple, and we have to adjust now. There's a period of adjustment at the moment where we have to use more complicated theories to explain the natural phenomena that actually observed.
But what is it that makes the wave different?
It is. So essentially, when you look at the tide gauge measurement of a storm, you see 30,000 waves arriving at the tide gauge, and they have varied amplitudes and varied wavelengths. Let's say they vary between 2 and 14 meter or something like that in a wave height from trough to crest, and the wavelengths varies from let's say 7 to 15. But all of a sudden you create something that is sustainable for like a minute or minutes, and there you come into trouble explaining this phenomena with this very simplified sort of discrete wave idea of arriving. And that's something that we need to change in our thinking, that these discrete waves generate, in their complexity, generate physical processes that can generate velocities that sustain for much longer than we actually would expect from a second or from a 6-second wave to be generated. These are very nonlinear processes and very complicated processes that are leading up to this observation. I mean, like and again, it's never been observed before. We know this minutes-long inundation from a tsunami really well, but if you look very, very sort of linear at a storm and a tsunami, you see like a 10-minute wave in a tsunami, and you see 30,000 short waves in a storm, and you can describe them with very simple theories, but then it turns out that nature doesn't like simple theories and makes it more complicated.
And another way of describing it is that the short waves that are offshore, when they break, there are processes which transform them into longer waves right at the shoreline, and that's what you see.
Do we have any other questions here in the room? Are there any questions from the chat? No. Okay, then I think we're done. Thank you very much, speakers, for your time and your interesting material, and thanks everyone for being here. Our next press conference is tomorrow morning. Oh, there it is. Looking under the ice, you can read it yourself. 8 a.m.